Welcome to Physics Latam High Energy and Mathematics Seminar. Today, we're honored to have Professor Susan Sierra, who will present the talk, One and Two-Side Ideals in Enveloping Algebras of Infinite Dimensional Lie Algebras. Professor Susan Sierra is a faculty member at the University of Edinburgh. She earned her PhD from the University of Michigan in 2008 under Professor J.T. Stafford. She held a postdoctoral position at the University of Washington and Princeton University, supported by NSF fellowships. Her research focused on non-commutative algebra and non-commutative algebraic geometry, infinite dimensional Lie algebras, and algebraic geometry. Professor Sierra has secured a major grant from EPSRC and NSF and received numerous awards. During the seminar, if you have any question, please use the raised hand feature on Zoom and I will give you speaking permission, or you can just send questions in the chat box. Now I'm pleased to hand over the session to Professor Susan Sierra. Thank you again for accepting our invitation.
Thank you very much for inviting me. It's a pleasure to speak at this school. And also a pleasure to be featured on the beautiful poster that Jesse designed, which features me juggling the root diagram of E8. So I feel like it's made me into some kind of superhero. It's fantastic. I'm a mathematician, so I'm going to give this talk as a mathematician, even though I know there are people in the audience who think more like physicists. So I'm just going to ask the physicists to bear with me that I'm sort of speaking mathematics rather than physics. So I'm going to talk about ideals in enveloping algebras of infinite dimensional Lie algebras. But let me be a little more careful with my title. I'm talking here about left, right, and two-sided ideals, and in the universal enveloping algebras of finitely generated infinite dimensional Lie algebras. And the ground field here is always going to be the complex numbers. Let me start by saying something about this word finitely generated. Since one of the main things I'm interested in is Noetherianity questions, that is, are these ideals I'm talking about, are they finitely generated? If the Lie algebra itself is not finitely generated, then immediately the augmentation ideal, the enveloping algebra, isn't finitely generated, so you lose any chance of finite generation properties for these ideals. So while in particular two-sided ideals in infinitely generated algebras are hugely interesting, I'm not going to go anywhere in that direction. All the Lie algebras in this talk will be finitely generated. So let me say a little bit about what I hope to do today. I'm going to lead off by giving some examples of the sorts of Lie algebras that are of interest. I'll then talk about enveloping algebras and remind you or tell you about some of the basic facts about enveloping algebras. And then I'm going to talk about one-sided ideals and then two-sided ideals in these enveloping algebras. We'll see when I talk about two-sided ideals that there are relatively few theorems about two-sided ideals and lots of conjectures. And the evidence for these conjectures comes from what's known as Poisson ideals in symmetric algebras. And so the last part of this talk, I'm going to be talking about Poisson structures on symmetric algebras, and particular Poisson ideals in the symmetric algebra, specifically of the Virasoro algebra. And we'll see that these have to do with what are called local functions. And so I'll end by telling you a bit about local functions. And I may or may not get through everything on this table of contents. And I'm guessing that there's going to be a break either right after part 3 or sometime in the middle of part 3. I'm not going to stress about having the break come exactly after 60 minutes, if that's okay, just roughly halfway through. Okay. One other piece of bookkeeping is that I'm going to use 2 different letters for Lie algebras, and roughly speaking, whenever I use capital L for a Lie algebra, it's going to be infinite dimensional, and whenever I use frac G, it's going to be finite dimensional, often simple. So just that will help remind you which kind of Lie algebra I'm talking about in the moment. Okay, so let's start with some examples of interesting infinite dimensional Lie algebras. So the fundamental example and the Lie algebra that we're probably going to spend the most time with in this talk is the Witt algebra, which is the Lie algebra of derivations of the Laurent polynomial ring in one variable, or if you like, the algebra of polynomial vector fields on the punctured complex line. So this is an example of a Lie algebra of derivations because it comes from derivations of some commutative ring. And for this audience, it won't be a surprise to know that actually even more interesting than the Witt algebra is its central extension, the Virasoro algebra. So this is, as a vector space, it's the Witt algebra and then one more generator, which I'll call Z in this talk. And the relations are that Z is central, and then the Lie bracket of two Laurent polynomials times del. I should remind everyone that what I wrote here, that del here is going to be my symbol for d by dt. So this bit of the Lie bracket on Virasoro is just the Lie bracket on the Witt algebra. And it comes, in fact, from the commutation relations in the Weil algebra, or if you like, from the product rule in calculus. This tells you how you should move a del past a polynomial. And then this bit here is, well, there's some complicated formula for some scalar times z. So usually when you take quite often when you take the Lie bracket of of an f del and a g del, you'll get some non-zero scalar times z. And this is a general machine for building central extensions of Lie algebras, where you can take a Lie algebra like W and then add on a one-dimensional central element Z, central component generated by Z, and then you have something that's called a two cocycle on your original Lie algebra, and that tells you how to add scalar times a Z component, so what you get is a Lie algebra. And the Virasoro algebra, of course, is an example that comes up all over the place in physics and in mathematics. It's important in representation theory. It's important in string theory. It shows up in two-dimensional conformal field theory. It's one of these objects that comes up all over the place and has unexpected connections with lots and lots of different things. And then generalizing these examples, I could take any commutative algebra C and then look at the Lie algebra of derivations on C, and that will give me another Lie algebra, usually infinite dimensional. Okay, so this is one class of examples. Then a second class of examples are Kac-Moody algebras. I think you've seen them in this course, but let me remind you quickly how they work. You start with an integer matrix, let's call it A, and then there's a formula to give you a Lie algebra in terms of generators and relations, and the relations are these generalized Serre relations that come from the matrix in some way that I'm not going to explain. And depending on the matrix, there's three kinds of Kac-Moody algebras. They can either be certain kind of matrix. The Kac-Moody algebra you get is just a finite dimensional simple Lie algebra. So in general, these generalize the finite dimensional simple Lie algebras that are the first Lie algebra examples most people see. You can also get what are called affine algebras, and then finally you can get what's called indefinite type. So for me in this talk, the affine algebras are the most interesting. So I'm going to shade the truth a bit, and I'm going to say that an affine Kac-Moody algebra, what it is it's a central extension of a loop algebra of some finite dimensional simple Lie algebra. So let me break that down. You start with a simple Lie algebra, I'll call it mathfrak G. You then form what's called the loop algebra of G. So that's just G, elements of G times Laurent polynomials, and then the Lie bracket on this is that if I have an x times a polynomial bracket with a y times a polynomial, I combine them in the only sensible way. I bracket x and y together, and then I multiply that by the product of the polynomials. So that's the loop algebra. That in and of itself is an infinite dimensional Lie algebra. but then I take a central extension of that with this c times z like we saw in Virasoro, and there's a 2 cocycle in there that makes this into a non-trivial central extension, which I'm not telling you about, but it has something to do with the killing form on G. And so I'm going to call that algebra G hat. For people who know about Kac-Moody algebras, you know this is not quite the Kac-Moody algebra associated to A, but it's close enough. It's actually the derived subalgebra of that Kac-Moody algebra. So I'm just going to call this, for me, it's an affine Lie algebra. And then other examples. Well, infinite dimensional Lie algebras are just a zoo. There's no hope to classify them. They can do all kinds of wild and crazy things. So I'm just going to say, well, this isn't even really a very good zoo. It's really a zoo with zebras and lions and tigers and elephants and polar bears and every kind of animal you can think of in the zoo. And some more we haven't discovered yet. So you might say, well, this is crazy world of infinite dimensional Lie algebras. And I've told you a reasonable amount about kind of some specific examples. Why are these fair examples to focus on? Well, the answer is that these Lie algebras show up as answers to a very natural question. There's a lovely classification theorem due to Olivier Mathieu, which says, let's take a Lie algebra and let's assume it's infinite dimensional. Let's assume it's Z-graded and simple. I'll define this later in the talk. Don't worry about what this means if you don't know. It's just a natural structure you want to put on a Lie algebra to give it a bit more structure. And further, let's assume that it's not too big, so it has polynomial growth. Again, we'll see the definition of this later in the talk. Then, in fact, these can be classified, and basically we've seen them. You might have the Witt algebra. You might have a loop algebra over a finite dimensional simple Lie algebra. Or you might have a Lie algebra of derivations of a polynomial ring. So a couple things to say. First of all, I'm lying slightly. Mathieu's actual classification says, well, you might have a twisted form of a loop algebra, or you might have some subalgebra that's close to this algebra of derivations. But basically, this gives you a sense of what this classification looks like. And then the more important point is that the examples I gave are, first of all, they're important. They show up as answers to a natural question. And secondly, in some sense, they're reasonably general, right? These are the algebras that one classified if you look at infinite dimensional Lie algebras with natural kinds of structure on them. Okay, so I've told you about Lie algebras. I now want to tell you about universal enveloping algebras. So I'm a ring theorist. And in particular, I like associative things. And Lie algebras, of course, are not associative. So if you like associative things, you can turn a Lie algebra into an associative ring, or an associative algebra, I should say, which is called the universal enveloping algebra. So what this is called U of G. And so what it is I take the free algebra of non-commutative polynomials in a basis of G, and then the relation you put on is that the commutator in the enveloping algebra, xy minus yx, is the same thing as the Lie bracket for any elements of the Lie algebra. And one of the reasons you do this is you've now created an associative ring, and the modules over this associative ring are the same thing as the representations of the Lie algebra. So the ring and the Lie algebra have the same representation theory, and if from an associative perspective, you've now changed your nasty non-associative object into a nice associative object with the same representation theory. So let me tell you some basic facts about the structure of enveloping algebras, and I realize this might be revision for a number of people in the audience, but I think it's worth going through. So the most basic theorem is the Poincaré-Birkhoff-Witt theorem, which I'll just call the PBW theorem. And what it says is that as a vector space, the enveloping algebra of the Lie algebra is isomorphic to the symmetric algebra of the Lie algebra, where the symmetric algebra is defined, for the purpose of this talk, to be a polynomial ring in a basis of the Lie algebra. So take some x's, could be finitely many, infinitely many, depending on the dimension of the Lie algebra. Take the polynomial ring generated by the x's, that's the symmetric algebra. So not only is the enveloping algebra as a vector space isomorphic to the symmetric algebra, but actually there's a machine to go back and forth between the enveloping algebra and the symmetric algebra, which is denoted by this GR. And we'll talk more about this GR machine later in the talk. And the key principle about enveloping algebras is that the enveloping algebra behaves no worse than the symmetric algebra. If you like, this is an example of the basic principle that non-commutative rings are nicer than commutative rings. So if you have a non-commutative ring that looks like a commutative ring, only I've tweaked it slightly to make it non-commutative, the non-commutative ring is going to behave at least as well as the commutative ring, and quite possibly a lot better. So let's see how this basic principle works for a couple of properties that you might want for a ring. So as a ring theorist, if I meet a ring in a dark alley, okay, the first question I'm going to ask is the ring Noetherian? So this is a condition, the founding genius of abstract algebra, Emmy Noether, is the person who really started exploiting its power, and it's named for her. And a ring is Noetherian if any one-sided ideal, so any left or right ideal of the ring is finitely generated. I mean, really, there's a left Noetherian and a right Noetherian, but for purposes of this talk, I'm just going to say Noetherian means Noetherian on the left and Noetherian on the right. So Noether proved that this finitely generated condition is equivalent to the ascending chain condition, which I'll just abbreviate ACC, on one-sided ideals of the ring. So let's take an infinite chain, I1 contained in I2 going up, of one-sided ideals of my ring R, and the ring R satisfies the ascending chain condition if for all of these chains eventually they stabilize. There's some n after which all of these i's are equal to each other. Most rings you see in, say in undergraduate mathematics are Noetherian. For example, polynomial rings in finitely many variables are Noetherian. But remember this key principle that says that the enveloping algebra is at least as nice as the symmetric algebra. Right? Suppose you've got a finite dimensional Lie algebra. Then the symmetric algebra, well, it's just a polynomial ring in finitely many variables, so it's Noetherian. So therefore, the enveloping algebra is therefore also Noetherian. So what you get for free is that if you have a finite dimensional Lie algebra, then its enveloping algebra is extremely well behaved. And in fact, it has all good properties you'd ever want from a ring, basically because polynomial rings in finitely many variables have all good properties you'd ever want from a ring. These are also extremely well studied. Many of the techniques of non-commutative ring theory were developed to be able to work out what the finer structure of these extremely well-behaved non-commutative rings are. Here's another well-behaved property. So it's that an algebra has polynomial growth. This says that it's not too big. So how do you measure the size of an algebra? Well, let's take a vector space, a finite dimensional vector subspace of my algebra. Let's look at the powers of the vector space under multiplication, and I want to bound the dimension of these powers of V by some polynomial function. So for example, if the algebra was finite dimensional, right, then had a dimension, say, d, then whatever v to the n is, it would have to have size smaller than d. So then this polynomial would just be constant. So that's a very baby example of polynomial growth algebra. And polynomial rings in finitely many variables, I guess possibly unsurprising by the name, have polynomial growth. And therefore, remember our guiding principle, if you have a finite dimensional Lie algebra, its enveloping algebra also has polynomial growth. On the other hand, here's a ring that doesn't have polynomial growth, polynomials in infinitely many variables. You can't bound, depending on how big the vector space you take, you need a different polynomial to bound the growth. I should also point out that polynomials and infinitely many variables are also not Noetherian. So from the perspective of this talk, polynomials and infinitely many variables doesn't have either of the sort of the well-behaved properties that we might want an algebra to have. So the motivational question for this talk and for much of my work in the past decade or so has been, what is the ring theory of an enveloping algebra, of an infinite dimensional Lie algebra? Remember I said that finite dimensional Lie algebras are extremely well studied, but the infinite dimensional Lie algebras are much more mysterious and much, much less is known about how they behave. And what do we know about it from our general principle? Well, we know that it behaves no worse than the symmetric algebra of this infinite dimensional Lie algebra, which is a polynomial ring in countably many variables, so badly behaved. So when I'm lecturing, I like to draw sort of thought bubbles on the board to tell the students kind of what I'm thinking as I try to come up with proofs. And at this point, I'm just confused. What I know about the enveloping algebra of an infinite dimensional Lie algebra is it behaves no worse than a badly behaved ring. In other words, I know nothing about it. So we need to work harder to find out anything about these enveloping algebras. So one thing I can do is tell you about growth of these enveloping algebras. So I haven't formally defined growth of a Lie algebra, but it's the same kind of thing. Remember, when we defined growth of an algebra, you looked at multiplying, taking multiplicative powers of vector subspaces of the algebra. For a Lie algebra, it's the same thing. You just look at how many bracketing things together. And if the Lie algebra itself has reasonable growth, polynomial or sub-exponential, then the enveloping algebra also has sub-exponential growth. Let me not define sub-exponential. Let's give you an example. Let's do the Witt algebra. So this has a basis given by powers of t times del. I'm going to call this element EI. It's useful to have a name. The PBW theorem, in its finer form, which I haven't stated, tells you that a basis for the enveloping algebra, the Witt algebra, corresponds to generalized partitions. So I look at these words in the E's where I always am increasing the subscripts as I go to the right. And so how fast do partitions grow? Well, it's a theorem of Hardy and Ramanujan that partitions grow like e to the square root of n. So the function that bounds the growth of this enveloping algebra is bigger than any polynomial, but smaller than any exponential. That's why it's called sub-exponential growth. Okay, so that's the basics of enveloping algebras. Let me tell you now about one-sided ideals. Just checking for questions. I don't see any. So one-sided ideals of enveloping algebras. And in this talk, that's really going to mean Noetherianity, because the fundamental question I can ask again about any ring is it Noetherian? That is, are the one-sided ideals finitely generated? And in fact, 50 years ago, today, or this year, in their book about infinite dimensional Lie algebras, Amayo and Stewart asked, does there exist an infinite dimensional Lie algebra with a Noetherian enveloping algebra? As an example, suppose you have an abelian Lie algebra. So this says that the Lie bracket is trivial, it's 0. Then the enveloping algebra and the symmetric algebra are the same, and the enveloping algebra is isomorphic to a polynomial ring, either in finitely many variables if the Lie algebra is finite dimensional, or in infinitely many variables if the Lie algebra is infinite dimensional. And we know that the polynomial ring is Noetherian if and only if it has finitely many variables. So, so there's no abelian examples for my own Stewart's question. So this, I would say, is the most important question in the theory of enveloping algebras of infinite dimensional Lie algebras, and it's still very much open, although I'm going to tell you a bunch about it today. And since the answer seems to be easy for abelian Lie algebras, attention got focused, relatively early on, particularly in a paper of Dean and Small in 1990 on the Witt algebra. Is the enveloping algebra of the Witt algebra Noetherian? Remember, non-commutative rings are nicer than commutative rings, and the Witt algebra is a much less abelian Lie algebra. It's a very non-abelian Lie algebra. Nothing in the Witt algebra commutes with anything else unless I'm taking the trivial bracket f del bracket f del, which we know has to be 0 by basic properties of Lie algebras. And it turned out, 23 years after this question got asked about the Witt algebra, that the enveloping algebra of the Witt algebra is not Noetherian. This was a theorem of myself and Chelsea Walton, proved in 2013. And I want to tell you a little bit about the proof. So one of the amazing things about this proof is that this question got asked specifically for the Witt algebra in 1990. The theorem wasn't proved until 23 years later, and in the interim, lots of people were thinking about it. But the answer to the question turns out to be sitting out there for people to look at all the time. So there's an obvious homomorphism from the enveloping algebra, the Witt algebra, to the first file algebra, which I'll write sort of cheekily as polynomials in T, T inverse, and del. This is cheeky because this is a non-commutative ring. Del and T don't commute with each other. Sorry, I'm failing to, there we go. The product rule in calculus tells you that del t is t del plus 1. And so this Weil algebra is really, it's the algebra of differential operators on Laurent polynomials. So what is this obvious homomorphism? Well, the basis for the Witt algebra is Laurent polynomials times del. And the Weil algebra is generated by T and del. So I just send a Laurent polynomial times del to a Laurent polynomial times del. And it turns out that the kernel of this map, which I'll call phi, is not finitely generated as either a left or right ideal. So in other words, we didn't have to answer this long-standing question by coming up with some crazy infinite dimensional infinitely generated left ideal no one ever thought of. It would in fact have been sitting out there the whole time for just people hadn't realized it. So how do you prove this? Well, you find a different homomorphism from UW to not to the Weil algebra, but to the Weil algebra adjoin another variable s, which commutes with anything. And this homomorphism sends f del to f del plus s times f prime, which turns out to be a homomorphism. And it turns out that if I look at the kernel of phi, little phi, take its image under big phi, then that image, you can look in the image of big phi, which is a badly behaved ring. It's not Noetherian, but it's a lot smaller than the enveloping algebra, the Witt algebra, and a lot easier to work with. And you have enough control to be able to tell that big phi of the kernel of little phi is not finitely generated as a left or right ideal. And of course, that tells you that the kernel of phi isn't finitely generated as left or right ideal of UW. And oops, and I see a plus has gotten here that shouldn't have gotten in here. Please ignore that. That's from an earlier draft of the talk. So after this theorem, which was a significant advance, then things kind of stalled for a while, and there was incremental progress. From the theorem, we could show that if you were a Lie algebra on Mathieu's list, then your enveloping algebra wasn't Noetherian. A very nice general result was proved a couple of years ago by my PhD student Lucas Bazaglo, showing that if you have derivations of any commutative infinite dimensional domain, I should have said, its enveloping algebra is not Noetherian. It's pretty easy to tell that infinite dimensional Kac-Moody algebras do not have Noetherian enveloping algebras. And then it wasn't clear what else you could do. But in May, a very lovely theorem was posted on the archive, which was a huge advance on this question. So this is by Andrusiewicz and Mathieu, the same Mathieu who classified those Lie algebras. And what they prove is if you've got an infinite dimensional Lie algebra satisfying two very natural structure conditions, then the enveloping algebra is not Noetherian. So what are these two conditions? First of all, I want it to be graded, and graded by z to the d. What that means is that L decomposes as a direct sum of finite dimensional pieces indexed by d tuples of integers that play well with the Lie bracket. So if I take the bracket of Ln and Lm, I end up inside Ln plus m. So this is certainly a nice structure to insist that a Lie algebra has. And then the other thing you want is that Lie algebra is simple. It has no non-trivial Lie ideals. So a Lie ideal is a subset I such that if I bracket it with anything in the Lie algebra, I end up back in the Lie ideal. And I want there not to be any proper Lie ideals. The only Lie ideals should be 0 at the Lie algebra itself. So how do Andrusiewicz and Mathieu prove this very lovely general theorem? Well, what they do is they take an arbitrary infinite dimensional simple graded Lie algebras. They make very many clever reductions using techniques that Mathieu used to classify Lie algebras. Mathieu's, in the original classification theorem, Mathieu's Lie algebras had more constraints on them. But these have enough constraints so some of those classification techniques still apply. You don't get a full classification, but you get enough to prove that the enveloping algebras aren't Noetherian. And eventually you reduce that the only Lie algebra you can't prove where the enveloping algebra is not Noetherian by general techniques is the Witt algebra. But you already know that the enveloping algebra, the Witt algebra, is not Noetherian. So therefore, so this is a lovely paper. What about the general question? Well, it's really, really hard. I mean, again, for an arbitrary Lie algebra, we don't know anything about it. It could be, it lives in some wild, crazy zoo of infinite dimensional Lie algebras. And one of the things that this Andrusiewicz-Mathieu theorem shows is that you really want some additional structure to be able to get some control over how Lie algebras behave. And without that, it seems very, very hard to prove, to answer the general question. Okay, so let me move on to talking then about two-sided ideals. But before I do, are there any questions about the one-sided ideal part? How essential is the simple hypothesis in what Andrusiewicz and Mathieu do? Yeah, no, you really need it. And so, in fact, I mean, they reduce to the weaker hypothesis that here, this I here, you can assume that I is a graded ideal by a very clever reduction. But then, so now, but yeah, no, they really do need it. I mean, is there hope there's a non-simple Lie algebra with an Noetherian universal enveloping algebra? So I don't think there's an infinite dimensional Lie algebra with a Noetherian enveloping algebra, but I don't know. I don't know how to prove it. Okay, let me move on and talk about two-sided ideals. And here I'm going to specialize to either talking about the Witt algebra, Virasoro, or talking about affine Lie algebras. And I want to go back to this diagram that showed up in the proof of non-Noetherianity of the enveloping algebra, the Witt algebra, because if you remember, two-sided ideals were involved in this proof, right? The kernel of little phi, showing up here, was the infinitely generated one-sided ideal. But if you look at it as a two-sided ideal, it's a result of Conley and Martin that it's actually principal, generated by a single element. And the same thing is true for the kernel of big phi. Another thing I want to tell you about this diagram is that the image of big phi and of little phi, both of them satisfy the ascending chain condition on two-sided ideals. And then the other thing just to notice is that the enveloping algebra, the Witt algebra, is huge. It has infinite growth, but the images of these homomorphisms are much, much smaller. So this is suggestive, and the heuristic it suggests is that two-sided ideals in U of W are big, right? They're big enough that when you factor them out, you get much smaller rings, and they're also big enough that in the examples we have, the lattice of two-sided ideals seems to be pretty controlled. And they're also big enough that this huge one-sided ideal, the kernel of little phi, is principal as a two-sided ideal, right? So this suggests three conjectures. Whoops, no, not yet. Let me first of all try to define what I mean by big here. So let's say an algebra has just infinite growth. First of all, the algebra itself has infinite growth, but if I take any proper ideal I and factor it out, the algebra I get has polynomial growth. So this tells you that ideals of R are big, right? I have a big algebra R of infinite growth, but if I factor out any ideal, then what I get is a small algebra that has polynomial growth. So the ideals are so big that when I factor them out, I knock my gigantic algebras down to something that looks like a polynomial ring in finitely many variables. And in 2019, Natalia Ayudu and myself were able to turn the heuristic that two-sided ideals in U of W are big into a theorem. It's actually more general than for U of W. If I take any central quotient of the enveloping algebra of Virasoro, so factor out any z minus lambda, that algebra has just infinite growth. In particular, that includes the enveloping algebra, the Witt algebra, which is what I get where I just factor out z. Okay, so we've got a theorem that says a precise statement of the heuristic that two-sided ideals in the enveloping algebra of the Witt algebra or of the Virasoro algebra are big. And now I start thinking, well, if two-sided ideals are big, well, first of all, there might not be that many of them. There might not be room to have a very complicated lattice of two-sided ideals. And also, it might be easy for them to be finitely generated, right? So take an arbitrary two-sided ideal, right? Pick finitely many elements in it. Those are going to generate a big two-sided ideal, since two-sided ideals are big. And the ideal they generate might be so big that it's actually equal to the ideal I first thought of. So this theorem makes one think, well, okay, maybe if two-sided ideals are big, then the ideal lattice in these enveloping algebras, should be well behaved. So here's 3 concrete conjectures that say about the ideal lattice of Virasoro, of the enveloping algebra of Virasoro. First of all, the conjecture that two-sided ideals are all finitely generated. In other words, that the enveloping algebra of Virasoro has ACC on two-sided ideals. A stronger version of this conjecture is that, in fact, if I factor out a non-trivial central element, so some z minus lambda where lambda is non-zero, then the algebra I get has no two-sided ideals. In other words, it's simple. And then a third conjecture, which is related to the second conjecture in ways that, let me just say it's related without explaining why, I guess the way I'll phrase conjecture 3 is that the Virasoro has no polynomial growth representations with a non-trivial central character. If I've got a polynomial growth representation, or irrep, of Virasoro, then Z must act trivially. So let me tell you about evidence for these 3 conjectures. Well, the first conjecture was ACC on two-sided ideals, or that two-sided ideals are finitely generated. So certainly the fact that two-sided ideals are big is, I think, some kind of moral evidence for that. And then using Poisson algebra, which I'll tell you about in the second half of the talk, there's some Poisson evidence for this conjecture. The second conjecture, which is simplicity, U of Vir factored by Z minus lambda is simple for non-trivial central characters lambda. Again, there's a Poisson version, which gives evidence. And then it's also true for the enveloping algebra of G hat, which I'll tell you about later. And the thing you should think here is this sort of, this looks a bit like the Virasoro algebra, but it's much less non-commutative. So since non-commutative rings are nicer than commutative rings, right? If this conjecture about algebras being nice is true for affine Lie algebras, then that seems to make it more likely to be true for the Virasoro algebra. However, this is about not getting evidence, I guess. The conjecture about ACC is actually false for affine Lie algebras. Their enveloping algebras do not have ACC on two-sided ideals. But on the other hand, Virasoro is much more non-commutative, so it's much nicer. So who cares if this more commutative algebra is badly behaved? Virasoro could still be well behaved. And then the third conjecture about polynomial growth representations, well, first of all, there's no known counterexample. And this is actually useful evidence because if you look in the literature for representations of Virasoro and search on the archive, just give yourself another 5 or 10 years to read all the papers that show up. There's an amazing number of representations of Virasoro that people have looked at, and all of them satisfy this conjecture. And it's also true if you insist that representations are finitely Z-graded, because those are classified, and the conjecture holds for them. Okay, so what I want to do now is I want to switch, since I was getting some insight for what might happen for Virasoro from affine Lie algebras, and a bunch of our evidence or lack for these conjectures about Virasoro came from affine Lie algebras. Let me switch and tell you about enveloping algebras of affine Lie algebras. So the first thing to know about enveloping algebras of affine Lie algebras is that they also have this just infinite growth property that we saw from Virasoro. So let's take a finite dimensional simple Lie algebra G, and let's look at the associated affine Lie algebra G hat, and let's look at its enveloping algebra, and let's factor out some z minus lambda. So this is the ring that is supposed to make you think it's something like enveloping algebra of Virasoro, only more commutative. And these also have just infinite growth for any scalar lambda. And then, very surprisingly, to me and to experts on representation theory of affine Lie algebras, it turns out that if I factor out a non-trivial central character, so some z minus lambda for non-zero lambda, the ring is simple. And I get 2 is a corollary of 1. So 1, once you know 2, 1 looks silly, right? If I factor out some z minus lambda, then the ring is simple. So it certainly has just infinite growth, right? But in fact, you need 1 to prove 2. So what you get from this theorem is an easy computation of annihilators for representations with non-trivial central character. So let's take some representation M. Let's assume that Z acts by some non-zero scalar lambda. Then the annihilator of M in the universal enveloping algebra has to be Z minus lambda. What's the proof? The annihilator of M is a two-sided ideal. By construction, it contains Z minus lambda, but part 2 of the theorem says that Z minus lambda is a maximal two-sided ideal. So therefore, that has to be the annihilator. And there was very little known about these annihilators except for Vijayacharya's thesis, 40 years ago, which computed the annihilators of Verma modules. So let me tell you a little bit about the proof of this theorem. And as I said, the simplicity part of the theorem follows from the just infinite part of the theorem. So the just infinite part of the theorem, well, this uses the same methods that Yudu and I used to prove the just infinite part for the enveloping algebra of Virasoro, but it's more difficult because things are easier for, and Virasoro is a central extension of the Witt algebra. In the Witt algebra, there are no non-trivial brackets, right? If x bracket y is 0, that means that x equals y. Or, sorry, I should here obviously have said that there could be a scalar involved here, which I left out, but let me get away with that. On the other hand, in the loop algebra, right, I could take any element of my underlying finite dimensional algebra G, and then x times t to the n bracket with x times t to the m is 0. So it's got lots and lots of commuting elements, so it's much more abelian. And in that sense, we know that the more commutative, the worse behaved things are, right? And so it's sort of surprising that you still have this just infinite theorem. In fact, when Rekha, Biswal, and I started working on this, we were trying to prove the opposite of what turned out to be the case. So what about the second part, the simplicity part? Well, you've seen the infinite dimensional Heisenberg algebra. And the infinite dimensional Heisenberg algebra, which I'll write here as spanned by h's indexed by z, where hi bracket hj is, of some multiple of h0. The point of this bracket, right, is that h0 commutes with everything, and hi commutes with everything except for h minus I. So this is the infinite dimensional Heisenberg algebra, and it's a subalgebra of any affine Lie algebra. And it's a subalgebra in such a way that the central element of the Heisenberg algebra matches up with Z in the affine Lie algebra. So what does that tell you? Well, that tells you, therefore, that if I take the enveloping algebra of the Heisenberg algebra and factor out some h0 minus lambda, that's a subalgebra of U of G hat factored by Z minus lambda. So let's take a non-trivial ideal of u of g hat factored by z minus lambda. I think that doesn't exist, right? Unless lambda is 0. So let's assume there is one and see what happens. And I want to factor it out and then look at the commutative diagram I get. So we know that this quotient here has polynomial growth by the just infinite part of the theorem. On the other hand, this here, well, it basically is the enveloping algebra of an infinite dimensional Lie algebra, and it has infinite growth. So that tells you that this diagonal map here can't possibly be injective. It's a map from a very big algebra to a relatively small algebra. So it's got a kernel, and the kernel, of course, is a two-sided ideal. But if lambda is not 0, then this quotient here is well known to be a simple ring. So I've just constructed a two-sided ideal of this ring, so therefore I must have lambda equals 0. So that's basically, that's the proof of simplicity. So a few remarks. First of all, it's quite easy to see, remember this question about polynomial growth representations of Virasoro? It's quite easy to see that the corresponding result works for affine Lie algebras. So G hat doesn't have polynomial growth representations with non-trivial central character. How do you see that? Well, again, let's look at this quotient of the Heisenberg enveloping algebra of Heisenberg that lives inside UG hat factored by z minus lambda. This is isomorphic to the infinite Weil algebra, if you want to talk about it in a different way, and it's well known that that doesn't have any polynomial growth representations. So of course, this can't have polynomial growth representations. And since the representation theory of G hat and the representation theory of Virasoro are related, well, at least that's some kind of maybe moral evidence for the conjecture about representations of Virasoro. Certainly if there were a polynomial growth representation of G hat, that would give me a polynomial growth representation of Virasoro. Then another thing is just to give credit to Alexei Petukov for so he and I proved a couple years ago in a paper we're hoping to finish this summer that enveloping algebras of affine Lie algebras do not have ACC on two-sided ideals. So even though they have this just infinite property, their ideal lattice is not as well behaved as one might hope. Okay, so I was talking about these conjectures about how the enveloping algebra of Virasoro behaved. Let me go back to that slide if I can. Yep. Right, so I had these conjectures about the enveloping algebra of Virasoro, and I was talking about evidence for these conjectures, and we saw that some evidence came from looking at affine Lie algebras, or some lack of evidence came from affine Lie algebras, but then a bunch of this evidence came from what I said were Poisson versions of the conjecture. So the other thing I want to do in this lecture is to tell you about that Poisson evidence and sort of the additional structure that one has on the symmetric algebra of an infinite dimensional Lie algebra. But this seems like a good moment to take a break. So let's take a break. Let's take a break now and then come back. What, Daniel? And so before going on to another topic, let me just ask if there's any questions from the first half of the talk.
So I believe this principle or heuristic about that non-commutative is better than commutative immediately. I just suspended my disbelief. And I believe that there are all these properties, but why? What's the reason? Why should I believe that? I don't know, other than the evidence. I mean, I was like working with these non-commutative rings. Mhm.
So, I mean, if you're interested in the kinds of questions that I've been talking about, these Noetherianity questions, right, then you want, I mean, so I tried to persuade you that finite generation questions are some version of saying you want one-sided or two-sided ideals to be big, right? But say two-sided ideal, right? If I've got an element x in a two-sided ideal, then x times r needs to be in it for any element of the ring. But if the ring's non-commutative and it's a two-sided ideal, right, then r times x also needs to be in there. So you get more elements in there, and so it's easier for two-sided ideals to be big. And slightly less obviously, for one-sided ideals, well, now if I have x and y in the one-sided ideal, right, then x, y, and yx need to be in the one-sided ideal. So again, one-sided ideals are also big. So I think that's really, I really think that's the reason why these, I mean, formally you have a non-commutative ring that's a deformation of a commutative ring. And it's a principle of deformation theory that if you take a nice object, nice here meaning almost any way you might make that specific, and deform it, it stays nice. Right. So this means that, you know, the non-commutative ring, this deformation of a commutative ring, is at least as nice as the commutative ring you started with. So that's maybe that heuristic expressed a little bit more precisely.
Yeah, that was really helpful. Thanks.
Okay. So let's move on then and talk about Poisson ideals. And here I really am going to be focusing on the Virasoro algebra. So we started talking about any infinite dimensional Lie algebra, and we've gradually been focusing in more and more. And so at this point, we're just talking about Virasoro. Let me just quickly go over or remind you about this extra structure that symmetric algebras of Lie algebras have. So let's take any Lie algebra L. Here's its basis, xi. And then the symmetric algebra of L we saw is just a polynomial ring in this basis. But it has extra structure. There's a Lie bracket on it, which is written with curly braces, that satisfies two properties. First of all, on the Lie algebra, this Lie bracket, this Poisson bracket, agrees with the bracket on Lie algebra, and then it's a biderivation in each variable. So if I want to take a polynomial, if I want to take a bracket of two polynomials in the x's, what do? Well, I use the Leibniz rule to deduce what the bracket looks like from the bracket just of the variables. So this is an exercise in calculus. And remember, I said that there was this GR machine that lets you get the symmetric algebra S of L as GR of U of L. And it turns out that the Poisson structures on the symmetric algebra are shadows via this GR construction of the non-commutative structures on U of L. And somehow what this tells you is the Poisson structure on the symmetric algebra remembers not all, but some of the non-commutative structure, and enough that knowing about the Poisson structure on the symmetric algebra tells you some things about the non-commutative structure on the enveloping algebra. So let me explain that more precisely. And I'm going to do this just for the example of the fit algebra, where we have a basis that we already like. Remember, these are these EIs that are t to the I plus 1 del. So I'm going to write the enveloping algebra of W as a union of subspaces, which I'll call U less than equal to K. And U less than equal to K of W is just the span of all words of length less than equal to K of the EIs. All right, so U less than equal to 1 is W itself together with the constants. And then I'm going to form what I'm going to call GR of U of W. Here's this mystery GR construction. as a direct sum of the factors of the words of length less than or equal to k factored by words of length less than or equal to k minus 1. So what does this GRU of W, what does it look like? I've just written it down as a vector space, but it turns out it has two algebraic structures. So to tell you what they are, let's take F. I'm just going to say that F is a word of length k, but in fact it's going to be a linear combination of words of length k that can't be written in terms as a sum of shorter words. And G is going to be a word of length L. And there's two ways I can combine gur F and gur G. They're images in this quotient over here. I can multiply them together. So gur F times gur G, I'll just define it to be gur of Fg. In other words, being a bit more precise, it's going to be the coset of Fg, which has length L plus k, with respect to all words of length shorter than L plus k. And this defines an associative and commutative ring structure on gur of UW. But the other way I can combine gur F and gur G is I can take their commutator, or take gur of their commutator. So here, gur of Fg is gur of Gf because it's commutative. So what that means is that if I take Fg minus Gf and try to take the coset with respect to k minus L plus 1, I'll get 0, right? Those agree, mod k minus L plus 1. But on the other hand, if I look at the coset with respect to the stuff of length k minus L plus minus 2, k plus L minus 2, I'm going to get something interesting. And that's going to define as the Poisson bracket on gur F and gur G. And this Poisson bracket, this is what I mean by saying the Poisson bracket is a shadow of the non-commutative structure. The Poisson bracket is, in some sense, the shadow of the commutator in the associative algebra. So these two structures define the structure of a Poisson algebra on S of W. Let me write that down because I don't think I did. Sorry, I should have said it satisfies a Poisson, the structure of a Poisson algebra on gur of UW, but we also saw that S of W is a Poisson algebra, and the PBW theorem says that those structures match up. So I keep saying Poisson structures are shadows of non-commutative structures. Here's an example. Let's take an ideal, two-sided ideal J of the enveloping algebra. Sorry, this normal triangle is my abbreviation for two-sided ideal. And let's take an element F of my ideal and just an element G, an arbitrary element of the algebra. Well, then, of course, the commutator of Fg and Gf is in my two-sided ideal, as I was just talking about. And that tells you that the Poisson bracket of gur F and gur G is in the image of J under this gur map. So in other words, if I have a two-sided ideal of U of L, then its image under gur is a Poisson ideal of the symmetric algebra. Remember, the symmetric algebra was gur of the enveloping algebra. So what does it mean to be a Poisson ideal? Well, it means that it's an ideal both with respect to the ring structure and with respect to the Poisson bracket. It's a Lie ideal with respect to that. And whenever I have something like that, I'm going to write this as gur J, or for any Poisson ideal, I'm going to write as triangle sub P of the symmetric algebra, just as my word for the symmetric algebra. I should have said, by the way, just going back, that why am I calling this gur? Well, this thing here is a direct sum of graded pieces, and in fact, this is a graded ring. So it's gur because it takes my non-graded algebra, enveloping algebra, it's filtered and turns it into an honest graded ring. And that's the reason for the gur notation. Okay, so we've seen that Poisson ideals in the symmetric algebra are shadows of two-sided ideals. In particular, every time I have a two-sided ideal in the non-commutative ring, I get a Poisson ideal of the symmetric algebra. So in particular, if I know that the Poisson ideals in the symmetric algebra are well behaved, say I have ACC, that will let me deduce, basically as an application of this general principle we've been talking about, that the enveloping algebra will have ACC on two-sided ideals. This is an example where knowing something about the Poisson structure will tell you something about the non-commutative structure. So one of the conjectures I had made about the enveloping algebra of Virasoro, or I claimed to get intuition from the Poisson side, was that the enveloping algebra of Virasoro has ACC on two-sided ideals. In other words, two-sided ideals of the enveloping algebra of Virasoro are finitely generated. Let's see what we can tell about this conjecture from the Poisson side. Well, this is a bit annoying. So what we have is a theorem. This is myself and Omar Leon Sanchez that came out in the first few months of the pandemic. If L is Virasoro or L is any Lie algebra on Mathieu's list, then its symmetric algebra has ACC, not on Poisson ideals, which would be fantastic, but on radical Poisson ideals. So these are Poisson ideals that are radical ideals of this commutative ring, which as a commutative ring, remember, is just a big polynomial ring. So this certainly is giving you intuition that maybe there's ACC on Poisson ideals, which would tell me that this conjecture was true. But it's not actually very good intuition, because this is true for G hat, right, which is on Mathieu's list. But we saw that the enveloping algebra of G hat does not have ACC on two-sided ideals. So this intuition actually is intuition, but as evidence is pretty worthless. But at least it gives you some kind of intuition, maybe, that might be helpful to look at two-sided ideals of the enveloping algebra of Virasoro. So let me move quickly on, since I'm not getting any useful intuition about conjecture 1, and ask about conjecture 2. So this is the conjecture that if lambda is not 0, then enveloping algebra of Virasoro mod z minus lambda is a simple ring. So here we get much more useful intuition. But to tell you the intuition we get, I need to tell you a bit more about Poisson structures. So if you have a Poisson algebra, let's call it S, one of the first questions you want to ask about it are what are the Poisson primitive Poisson ideals of S. So let me explain to you what a Poisson primitive ideal is. So if I got a Poisson ideal, let's call it P, it's Poisson primitive if it's the Poisson core of a maximal ideal. Okay, so let's break that down. I take a maximal ideal of S. So I should have said that all my Poisson algebras are going to be commutative rings. So here, this is just a maximal ideal in this commutative ring. And inside this maximal ideal, I take the largest Poisson ideal contained in M. And that is, by definition, the Poisson core of M. And why are these interesting things to look at? Well, one way to get a Poisson algebra is a symmetric algebra of a Lie algebra. So let's assume that I've got some Lie group, capital G, and it's Lie algebra, little g, and I take that symmetric algebra. Then the Poisson primitive ideals of the symmetric algebra of that Lie algebra are the same thing as the defining ideals of coadjoint orbits in G star. So that is orbits of the Lie group acting on the space of functions on G. So if you think coadjoint orbits are interesting, which they are, one way to check that is to type coadjoint orbit into MathSciNet and see how many hits you get. It'll be a lot. Then that's evidence that these Poisson primitive ideals might be interesting as well, because they sort of generalize coadjoint orbits. So let's now think about what we get for symmetric algebra of Virasoro. So first of all, the first thing I want to talk about Poisson ideals in the symmetric algebra of Virasoro is a Poisson version of the just infinite theorem. This was proved by myself and Natalia Ayudu at the same time as the non-commutative version. So this is basically the same theorem, except I added a bunch of p's to it, right? So take the symmetric algebra of Virasoro, factor out some z minus lambda, take a non-trivial Poisson ideal, then the quotient here, again, has polynomial growth. In fact, this is how we proved that just infinite for the enveloping algebra. We proved it first for symmetric algebra, and then we used the principle that the enveloping algebra is nicer than the symmetric algebra. So because this, so what does this tell you? Well, let's take a non-trivial Poisson ideal of the symmetric algebra of Virasoro, and let's furthermore have one that strictly contains some z minus lambda, right? Then that tells me that I should expect to be able to do some algebraic geometry on the vanishing locus of this ideal, thought of as a collection of maximal ideals, and maximal ideals in the symmetric algebra correspond to functions on the Virasoro algebra. So why do I expect to be able to do some algebraic geometry? Well, when I quotient out I get an algebra of polynomial growth. That tells me that this V of I should be finite dimensional, even though a priori there's no reason to expect it should be finite dimensional. It lives in some very large infinite dimensional space. And also we've got this ACC on radical Poisson ideals, and that tells you that this Poisson ideal can only have finitely many irreducible components. So you can do algebraic geometry in sort of like finite dimensional algebraic geometry here, even though a priori you might not expect to be able to do that. So how does that help you to work with functions on the Virasoro algebra? Well, let's take a function on Virasoro. Let's call it chi. This is a function from Virasoro to C. This corresponds to a maximal ideal of the symmetric algebra. So hiding out here is an application of the Nullstellensatz, for those of you that know some algebraic geometry, which still works in this situation because the cardinality of the base field is larger than the vector space dimension of the algebra. This is why I'm working over the complex numbers. It's not helpful not only to have my field be algebraically closed, but also to have it be uncountable. So I've got my function on Virasoro. It corresponds to a maximal ideal of the symmetric algebra. And let's define P of chi to be the Poisson core of this maximal ideal. And let's now define the pseudo-orbit of chi, which I'll call Blackboard bold O of chi, to be all the functions nu, or eta, sorry, it was eta first and then it became nu on the other side of the slide, sorry about that. All the functions eta with the same Poisson core as chi. So this is, I'm calling it a pseudo-orbit because it's supposed to be some analog of the coadjoint orbit of chi, even though Virasoro famously does not have an adjoint group. And then, in fact, the vanishing locus of this Poisson core, this P of chi, is some kind of orbit closure, pseudo-orbit closure. And again, I expect I should be able to do some algebraic geometry with this pseudo-orbit closure. So that's, I guess this is just setting up some machinery and being a bit hand-wavy about why I expect it to tell me something useful. Again, if you have any Poisson algebra, you want to be able to figure out what the Poisson primitive ideals are. And in fact, we can answer pretty much every question about Poisson primitive ideals of the symmetric algebra of Virasoro. This is a paper of myself and Petukov from 21, which has now been published in Compositio. So we can classify the Poisson primitive ideals of Virasoro. So in particular, one of the things you want to know is what are the functions that have a non-trivial Poisson core. So if I have a function chi, then z minus chi of z generates a Poisson ideal. Z is Poisson central, Poisson commutes with everything, so the ideal generated by z minus chi of z is a Poisson ideal. This is certainly contained in the maximal ideal associated to chi, and so it's contained in the Poisson core, and then you want to say, well, a function has an interesting Poisson core if it's a strict containment, if something else is in the Poisson core, if there's more stuff. And we know exactly when, for which functions this has an interesting Poisson core, and one of the really surprising things we get is this happens if that, the only way that happens is if chi vanishes on z. This is very striking and certainly surprised me. And from that, we get that if lambda, if I factor out a non-trivial z minus lambda, so factor out z minus a non-zero scalar, then the symmetric algebra of Virasoro mod z minus lambda becomes Poisson simple. That is, it has no non-trivial Poisson ideals. So let's see why this is a corollary of the theorem. So suppose I've got some z minus lambda and then some Poisson ideal which strictly contains that z minus lambda. Let's call that Poisson ideal I. So any ideal is contained in a maximal ideal. I'm not doing any Poisson stuff here. I'm just doing basic ring theory. This maximal ideal is m chi for some chi. So then the Poisson core of chi is the biggest Poisson ideal contained in m chi, and it certainly contains I, which by assumption is bigger than z minus lambda. So in other words, the Poisson core of chi is bigger than z minus lambda, but the theorem says that forces chi of z to be 0. When you unpack this, chi of z here has to be lambda. So this tells you that in order to have non-trivial Poisson ideals, I have to be factoring out z. Factoring out z minus anything else, I don't have any Poisson ideals. So now let me tell you kind of the summary of everything we know about Poisson ideals of the symmetric algebra of Virasoro. I said we could classify the Poisson primitive ideals. I showed you that z minus lambda is a maximal Poisson ideal if lambda is non-zero. And let me remind you that one of my questions for Virasoro was, is the enveloping algebra of Virasoro mod z minus lambda simple for lambda is non-zero? All right. So this question 2 here certainly I feel like strong moral evidence for that conjecture, even though that conjecture, this conjecture or question here annoyingly doesn't actually follow from this theorem. Furthermore, we can parameterize the prime Poisson ideals of the symmetric algebra of the Vid algebra. No interesting Poisson ideals for any other scalar lambda, so I might as well just look at S of W. And furthermore, the pseudo-orbits are actually orbits of honest algebraic groups, although the exact algebraic group depends on the function chi. So I'm not going to tell you about all of this theorem because there's a lot here. Instead, let me try to tell you, a bit about the classification of the Poisson primitive ideals. So part 1 of this theorem. Well, actually, before I do that, let me give you a corollary, a related result, which is a strong structure result for the Virasoro algebra and is purely Lie theoretic. So maybe this might persuade you that this Poisson stuff is interesting, even if all you care about is Lie algebras. It turns out, again, this very powerful result, that if you have a finite codimension subalgebra, I should have said here that L here is a Lie subalgebra of Virasoro, then it has to contain Z. In fact, Z has to be contained in the derived subalgebra of L. So this was previously known for codimension 1 subalgebras, basically by hand. This is much more general. And we also have a structure theorem for finite codimension. We have a finite codimension structure theorem for finite codimension subalgebras of Vit and of Virasoro, which is that they look like I mean, the Witt algebra basically looks like Laurent polynomials, right, times del. And then the finite codimension subalgebras just look like ideals in this Laurent polynomial ring. And then a similar thing for finite codimension subalgebras of Virasoro. Okay. Right. So to tell you, I said I wanted to tell you more about the Poisson primitive ideals, and to do that I have to tell you more about functions on the Virasoro algebras. This is the last part of my talk, which is about local functions. So this is a theorem, it's in that paper of myself and Batukov. Let's start with a function on the Virasoro algebra. Now, I'm interested in Poisson primitive ideals, so the thing I want to know about this function is, does it have an interesting Poisson core? So these two very quick to see their equivalent conditions. Is the Poisson core different from z minus chi of z, or does the Poisson core strictly contain z minus chi of z? So there's three other conditions on the function that are equivalent to this having this non-trivial Poisson core. The second equivalent condition is the pseudo-orbit is finite dimensional. The third equivalent condition is that the orbit of Virasoro on the function is finite dimensional. And this is the formula that tells you how a Lie algebra acts on functions on the Virasoro, on the functions on the Lie algebra, right? So I need to take an element y of my Lie algebra and a function chi. I need to combine them to get another function. So what do? Well, I have to apply it to another thing here. I first bracket with y, and then apply chi. And that gives me a number, so that gives me another function on my Lie algebra. So the third equivalent condition is that the Virasoro orbit of chi is finite dimensional. And then the fourth equivalent condition is the really interesting one. First of all, the chi has to vanish on z. And then on functions, chi is a linear combination of just takes f del to, well, it takes some derivative of f and then plug it in, plug in some point. Here, p is just some point in C star. I'm plugging in. So these are called local functions because I'm measuring local behavior at a finite collection of points. And these are the only functions with interesting Poisson cores. So I'm not going to prove this in detail, but I'll tell you a little bit about the proof of this theorem. Why these four conditions are equivalent, or 4.5 conditions, if you think 1 and 1 prime are different. So 2 is the pseudo-orbit is finite dimensional. 3 is that the Virasoro orbit is finite dimensional. It turns out that it makes sense to think of the Virasoro orbit of chi as a tangent space at chi to the pseudo-orbit. So it makes sense that if one of them is finite dimensional, the other one should be finite dimensional as well. Then 1 implies 2. 1 is having a non-trivial Poisson core. 2 is that the pseudo-orbit is finite dimensional. This is the just infinite Poisson theorem. So what did that say? It'll remind you that if I've got a Poisson ideal which strictly contains some z minus lambda, then the quotient has polynomial growth. And you combine that with the observation that the way to calculate the dimension of the pseudo-orbit is by looking at the growth of the symmetric algebra factored by the Poisson core. So that tells you if the Poisson core is non-trivial, then the pseudo-orbit needs to be finite dimensional. And then what about for 4, which is the really interesting part, right? That said that, well, if I have the functions that have interesting Poisson core are these local functions. Well, first of all, you prove a similar theorem for the Witt algebra. So you look at functions on W. And again, you can define a local function on W in the same way. You now don't need to say that it sends Z to 0. There isn't a Z. But it looks like a linear combination of some derivatives. And it turns out that you can show that if a function is local, there's a bunch of equivalent conditions, but one of them is that the dimension of the W orbit of chi is finite dimensional. And then that lets you prove a structure theorem for finite codimension subalgebras of W, basically by looking at the details of this equivalent conditions, you get that they have to contain ideals, these things that look like ideals in the ring of Laurent polynomials. I realize I'm rushing through this a bit, and I'm sorry, but I think it's better to give you an overview than to try to do the details. And then from that, you get the structure theorem for finite codimension subalgebras of the Virasoro algebra. So the order in which you prove these things is definitely, you first prove A, then that tells you B, and then you prove C. So now let's go back to these equivalent conditions for functions on the Virasoro algebra. So 2 was the pseudo-orbits are finite dimensional, and 4 was that the function is local. So let's take a function on the Virasoro algebra, and I guess I was assuming 2, whoops. So 2 is that the dimension of the pseudo-orbit is finite, but we saw that was the same thing as 3, which is the dimension of the Virasoro algebra. Orbit is finite. But, I mean, by the orbit stabilizer theorem, the Virasoro orbit of chi is the same thing as Virasoro factored by this is the isotropy subalgebra of chi, which I realized was on the previous slide, and I just went by it. So the isotropy subalgebra, this is written for W, but it would be the same thing for Vir, is, it would be the stabilizer subgroup if this were a group, but because this is Lie algebra, you want the set of Y that act trivially on chi. And I have this function chi with a finite dimensional pseudo-orbit that tells you the isotropy subalgebra has finite codimension because the quotient is the Virasoro orbit of chi. But I've just given you a structure theorem for Lie subalgebras of Virasoro of finite codimension. And in particular, they all contain Z in their derived subalgebras. So this tells you that Z is in the derived subalgebra of the isotropy subalgebra. And when you unpack that, that forces chi to vanish on Z. So now chi is, well, it's a function on Virasoro that vanishes on Z, so I can think of it as a function, therefore, on Virasoro mod Z, or a function on W. Right? But then I've proved a structure theorem for functions on W that have interesting pseudo-orbits, and I know that they are local functions. So this now, once I force chi to vanish on Z, in other words, then I'm just back to the structure theorem for functions on the Witt algebra, which I claimed, didn't really prove. So I think, yep, so this is basically what I had planned to say. So let me wind up just with a recent result and some questions that this analysis of Poisson ideals leaves us with. I gave you a theorem back before I got into the local function section. I gave you a theorem about Poisson ideals in the symmetric algebra of Virasoro, and I said we know an immense amount about Poisson ideals. This is definitely true, but notice that all the Poisson ideals we know something about are prime, or by extension, radical. Poisson primitive ideals have to be prime. So we already knew that symmetric algebra Virasoro satisfied ACC on radical ideals. So in that sense, all this wonderful stuff we proved doesn't give us any new information if we care about finite generation questions. So it's easy to see that if S of W has ACC on Poisson ideals, that's equivalent to S of Virasoro satisfying ACC. Is this true? And of course, if we knew this were true, then that would tell us that the enveloping algebra of Virasoro has ACC on two-sided ideals, which is something that that is a very interesting open question. Then we have all the structure theory for Poisson primitive ideals. What about primitive ideals of the enveloping algebra? So here, let me remind you, these are annihilators in the enveloping algebra of simple modules. This is one of, okay, if you're a ring theorist and you meet a ring in a dark alley, the first thing you want to know is it's Noetherian, and then the second thing you want to know is probably what are its primitive ideals. So this is another very fundamental ring theoretic question. So a little bit of progress in this direction is that you can generalize the orbit method for finite dimensional solvable Lie algebras to the Virasoro algebra. This is something that my PhD student Tuan Pham is working on. So in other words, you can go from Poisson primitive, let's get back to that. You can go from Poisson primitive ideals of the symmetric algebra of Virasoro, which by definition correspond to pseudo-orbits, to primitive ideals of the enveloping algebra. But then the question here is this surjective? Are all the primitive ideals you get, are they the primitive ideals that you get from these Poisson primitive ideals? That's true for finite dimensional solvable Lie algebras. Virasoro is not finite dimensional solvable Lie algebra. And let me point out, by the way, that this conjecture that U Virasoro factored by Z minus lambda is simple for lambda non-zero, right, is, if you like, a special case of the surjectivity here, right? If there's some lambda where U Virasoro mod Z minus lambda is not simple, well, then that ring has primitive ideals, which definitely don't come from Poisson primitive ideals, because the Poisson primitive ideals all come, the interesting ones all assume that lambda equals 0. So I started this talk by saying, well, enveloping algebras of finite dimensional Lie algebras are some of the most well-studied non-commutative rings out there. And in contrast, enveloping algebras of infinite dimensional Lie algebras are much more mysterious. Almost all the theorems I put up here have been proved since 2013, right? It's an area where there's many, many more questions than there are theorems. So in that sense, it's a fantastic area to work in. And if anyone is interested in working on any of this stuff, please do get in touch. It's a great area. I think this is what I had, so I'm gonna stop here a bit early and just see if there are any questions. Thanks very much.